Good afternoon, Ian. How's it going?
Um, good. What? What about you?
I just had my final exam yesterday. It went well, but I know I'm not going to get 100%. So I'm a little upset because I got 100% on the last test.
Yeah.
Um, is your school semester over yet? Are you there, buddy?
Mm,
Are you ready to talk about some math?
yeah.
All right. So first I need to ask you, do you know what a vector space is? Let me give you an example of a vector space, okay?
Mm-hmm.
So if we have size n lists of natural numbers, then actually let me say something else first. Let me show you just an amazing computational fact that is extremely connected to what we did last time. Okay, so I want to make a Pascal matrix, right? So 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 3,
Wait,
3.
I can't see your screen.
Oh, that will probably help, won't it? Okay. 4, 5, 6, 10, 10, 20. That's going to be 15, 15, 35, 35, and the final one is 70, correct? Do you
What?
want to take a guess at what the determinant of this matrix is? So let me call this matrix
Okay.
P, and I, Jth. What are you confused about there, buddy?
No, 6. I think that's the determinant.
You think the determinant is 6?
Yeah, because it's in the middle.
Okay, let's call this P5, okay? And the Pn matrix, P for Pascal, is for 0 less than or equal to I comma j less than or equal to n minus 1.
Where
That,
n is.
the dimension of the matrix.
Wait, can you have a 4 by 5 Pascal matrix?
Nope.
Or
You can't.
3 by
Well,
2?
nope.
Or 3 by 3?
3 by 3 is correct. So this would be the 3 by 3 Pascal matrix right here, right? And this would be the 4 by 4 Pascal matrix in here, right?
Oh, that's cool that they're inside each other.
You want to know something else that's cool?
What?
The determinant of Pn is always equal to 1.
Wait. That's the answer for P5. What about P3?
It's true for P3. Let's compute it for P3. This is an amazing claim, right?
It's kind of like a half of a Pascal's triangle.
It's kind of like a what, buddy?
A half of Pascal's triangle.
There are definitely some missing parts. But why do you say that?
Because if you take this part and repeat it to get 5 ones. and then 1, 2, 3, 2, 1, and 1, 3, 6. 3, 1. Well, if you just remove some extra stuff, you'll get a Pascal's triangle.
Yeah. So it's like a little bit less than a half of a Pascal's triangle, right? Because this is a Pascal's triangle, and then we have like another triangle piece here, but it's not quite half of one, right? So,
because the Pascal triangle is symmetric.
It is symmetric.
Of every number as what color.
So this is proving this is off in the distance. This is something I want to aim for.
Every single number is in the Pascal's triangle.
That's true. What does this have to do with calculus? Well, let me tell you the first step to proving this thing in blue, which is also going to be our connection to calculus, okay? So I'm going to do this for P4.
Wait.
But the pattern that I'm going to write is true.
P3?
I want to do it for P4. P4 is a good size to be able to see patterns, but not to waste our time. So this is actually equal to a product of two other matrices. And
are those two matrices P3 and P3?
Not quite. P3 is a 3x3 matrix. So a 3x3 matrix times another 3x3 matrix is going to be a 3x3 matrix. There's no way you can get a 4x4 matrix out of it. But these are very related to P.
What is a P? What is P3? Wait, what is P3 times itself?
That's a very excellent question. And I'm going to leave it up to you to figure out what's going on there for me. But before I tell you what's on these two parts of these matrices that it factors into, I want to say that since this matrix has a diagonal of 1s and 0s above it, the determinant of this matrix is 1. And since this has a diagonal of 1s and 0s below it, the determinant of this matrix
is 9 minus 1.
No, it's also 1.
Well,
they're
if
both
it's
1.
Below, then it's minus 1.
No, that's actually incorrect. It's a plus 1. This is a plus 1. The determinant is plus 1.
If you have matrix A times matrix B equal to matrix C, is the determinant of A times the determinant of B also equal to the determinant of C?
That is 100% correct. And I would like to prove that theorem for you eventually. So this is a very good example of a lot of different tools that we need to prove interesting stuff like this. So I'm hoping just to catch your interest. Yeah, what is in these parts? Well, you tell me if you recognize this.
It's similar to P3.
All right, we should confirm that this is true for this example, right? So I'm going to do this product right here.
Let's do P3 next.
Let's do P3 actually. So let me give a name to this. This is called the P equals LU factorization, okay? So it's a lower triangular matrix, L for lower triangular, and U for upper triangular.
I thought it meant left and up.
Not quite. Also, this right here is the tool that
what, the upper triangular?
Yeah, the upper triangular. We're going to see this again in derivatives. Need for algebraic derivatives.
Triangular is like a twin.
Sorry?
The lower triangular is like its brother because it's flipped around. It has the same determinant.
Yes, and it's going to we're going to see very beautiful things that because they're true for you, they're automatically true for L as well. Okay.
What if you know they're true for L, but You want to see if they're true for you.
I'm sure that the proof would be exactly the same, and we're going to see a bunch of symmetry Y. So what do these things have to do with what we were talking about last time? So let me remind you that last time we thought of this polynomial, instead of writing it out this way, buddy, I want to start using new notation. So instead of writing it this way,
What notation?
I want to write it like this. The sum from I equals 0 to n of ai xi. Okay?
AI.
ai xi. Have you seen this notation before?
Yeah, I have seen the E notation.
All right, so this is the notation that I would like to use now. I also want to make a comment that if I just wrote ai xi with n implied, this is called Einstein notation. And the way that you...
Did you actually write n implied below it?
Yeah. So this isn't actually, no one writes n implied, but what you see is if you have two of the same number, one upstairs and one downstairs, what it means is sum over I from 0 to n. That's what the n implied means, is you assume that when someone's reading it, they know what the dimension is. Okay, so I want you to notice something, that if we call this a of x, and let's say we call alpha of x equal to alpha 0 plus, here, I'll actually just write it using this sum from I equals 0 to n of alpha I x to the I, then what we can conclude from this is that polynomials of degree at most n, okay, so that's kind of important, at most n, form a finite dimensional vector space. What does this mean? What does that mean? Okay, what does that mean? So this is what it means, is that so we're gonna have 8 rules, okay?
8 rules or 8 rulers?
8 rules, 8 or 9, actually 9 properties that completely determine a vector space. If something has these 9 properties, then it's a vector space. 9
properties define a 9-dimensional vector space?
No, you'll see. So
whoa.
Property 0 is that if...
I like doing property 1 stuff first.
We're starting at 0, buddy. Didn't we start at 0 earlier?
Okay. Well,
if a of x and alpha of x are polynomials, so is a of x plus alpha of x. All right, very simple property. We're talking about them just for polynomials, but normally they replace that with vectors when they write the axioms of the properties of vectors.
I like doing it a of x plus b of x or alpha plus beta.
Okay, I'm going to use b for different polynomial later, but I'll use b for now.
Something else.
I want to use b, but we can use b for now. That's fine. So, and then property 1. Sorry, we want 1. Property 1. A of x plus b of x equals b of x plus a of x.
That's pretty obvious.
Yeah, but a vector space needs to have this property in general. So we're just listing all the properties that we need in order to identify a vector space. Okay. I'm sorry if this is a little obvious, but if we have these properties, then some really nice things happen, which you may or may not be familiar with. So then we have associativity, obvious again. And this should be really obvious for polynomials, but I want to use a tool from vector spaces is what it comes down to. Okay. So Then we have something called the zero polynomial, such that a of x
A of x plus z of x.
plus, let's call it 0 of x.
0 times x.
Yeah. Well, no, we're going to say where 0 of x is equal to the sum from I equals 0 to n.
0 of x makes it look like 0 times x.
I know. You're gonna have to bear with me though. You're just gonna have to.
I'll just call it O of x. You know what?
Okay, O of x, but all of its coefficients are 0. That's the 0 polynomial. Property 4. 0 times any polynomial is equal to 0. The 0 polynomial. Yep. That's actually how we should say it. Okay. Finally, 1 times any polynomial is equal to that polynomial.
And 2 times any polynomial is equal to that polynomial plus that polynomial.
Well, yes, but that actually is a consequence of this next axiom that we're going to write. And that is for any number alpha. So alpha is a number.
Alpha's a number, got it.
Times a of x plus b of x. That's equal to alpha.
It just says b with no number.
Alpha b of x.
It actually, the property that you just wrote just says b.
My apologies. And I actually skipped one. So this is technically the 7th property. Let me state the first or the 6th property. The 6th property is that if we have alpha and beta, and we multiply those first, and then multiply a polynomial, that's the same as if you did beta first and then alpha. Okay, so then the final property of a vector space is that alpha plus beta times
the square root of 3. Why does it say the square root of 3?
Where do you see the square root of 3?
Look, the square root of 3.
No, that's a beta.
What's so special about square root of 3 in this vector space?
There is nothing special about square root of 3. That's a beta. All right, so the nice thing about vector spaces is okay, so let's take an example of the plane. The plane is a 2D vector space.
You mean an airplane?
Okay, so I'm going to say that vector E1 is equal to 1, 0, and vector E2 is 0, 1.
And E3 is...
And if I had any vector V, which is just equal to x, y, then I could write that as x times E1 plus y times E2.
Wait a minute,
and this is unique.
Property?
We started at 0. 0 to 8. Okay, so if any vector can be...
What if that's a square root of 3 instead of a times symbol?
It's an x. Any vector can be written... I should say any vector in the plane can be uniquely written in terms of E1 and E2. We use this fact all the time.
But we just don't know it.
Yeah.
We don't know that we use it.
It's almost so basic that we don't have to mention it, but we're going to look at something. So this is an example, right, of what I wanted to talk about.
What about a 9D vector?
What this means is that, one second.
What about 9D vector space?
I'll talk about a 9D vector space right after this. The set E1, E2 is a basis for the plane. What that means is that every vector can be written uniquely in terms of E1 and
Actually,
E2.
what if your vector you're dealing with is 3 minus 2? Then I'll have to have 3e1 minus 2e2.
And that's
which
the
is
only
not
way to do
allowed
it, right?
Because you're not allowed to have differences.
Yeah, you are. When you multiply a vector by a negative, it means just flip it around. Make it point in the opposite direction. Does that make sense?
Yeah.
Okay. So, however, there can be more than one. Once you have a basis, there's only one way to write each vector. However, there can be more than one basis.
Because what if you have 2 times e1 and 2 times e2?
Or how about this one? E1 plus E2 and E1 minus E2.
Ooh, better idea. What about E1 and E1 minus E2?
Okay.
Is that a valid basis?
That is a basis. So how do we tell when something is a basis or not? So let me give you an example of something that is not a basis for 3D
E1
space.
to E1. Hold up.
E1 to E1. Okay, so we need this equation called the okay, so
There. That's what you wanted. That's
a set of vectors, let's say V1 through Vn, right, for an n-dimensional vector space, forms
I thought you were talking about
a
9-dimensional vector
basis,
not 90-dimensional vector spaces.
form a basis if the only solution. Oh, our friend Matt is going to join us. Hey, Matt. I'm just catching Ion up really quick on bases, on what the best basis is, and then we're going to talk about how the upper triangular matrix for our Pascal matrices is a change of basis matrix for Taylor series.
What about 9-dimensional? I want 9-dimensional vector spaces and not n-dimensional vector.
All right. I'll write a 9 here. All right, so we got a 9. If the only solution to A1 V1 plus dot 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 plus A9 V9 equaling the 0 vector. Let's see what Matt said. Oh, don't worry about it, Matt. This is completely optional. Don't even sweat it. So if the only solution to this equation is A1 equals A2 equals dot 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 equals A9 equals 0, then this set forms a basis.
Wait, what?
All right, so we're saying I want to use these arrows to go nowhere. So let me give you an example in the plane is if you have 3 vectors, this one, and
this one.
That one, right? I can make a path that takes me back to the origin out of these, right? I can make a loop basically.
Hold up. Wait. What?
So if I call this V1, V2, V3, then we have V3 minus 4V2 minus 2V1 is equal to 0, right?
Are these 2 vectors a valid basis?
Yes, they are.
If they're both pointing from the origin?
Yes, they don't have to technically be at the origin, but we always can move a vector.
How do you make a loop then?
For this one, you can't. They're a basis. If it's not a basis, then you can make a loop. So it's only a basis if the only way to go nowhere is to do nothing.
So are these things bases?
The ones that you drew are.
And what about the red and the pink one?
Those are not a basis because you could do the red and then you could do the pink and then you could do a shorter version of the pink and you could end up back where you started, right?
Or you could just do a longer version of the pink.
Or you could just do a longer version of the pink. Exactly, correct.
And what about the blue and the yellow?
The blue and the yellow are a basis.
Okay, then this is, wait, they're at a right.
They don't actually have to be at a right angle.
They're not at a right angle.
Okay,
Right.
so let me talk about two. So let's return to our example. Polynomials of degree at most n. Let's see, what do we have here? All right, yeah, Ian, Matthew has good insight. So just read anything that he says. So polynomials of degree at most n form a vector space. So
what is n?
N could be 5. N is a natural number. How about that?
That means that is a bad definition because it's assuming that it could be 0.
Well, if it's a natural number, then actually it can't be 0.
Actually, 0 is a natural number.
That's a very controversial definition, but Ian, you do coding, so I understand. So then actually that's fine. We can think of numbers as a constant polynomial. Right?
Yeah.
Okay,
because
so
9, for example, would just be 9 next to the 0.
Can you tell me what a basis is then? So if AX is a polynomial, what's a basis for a polynomial?
A basis for a polynomial?
Can you think of some simple polynomials that could be a basis? Let me write it this way.
Let me think.
This is a hint.
What about 3x squared plus 1 and x squared minus 1?
That would actually not be a basis.
Why not?
Because there's no way to write.
Oh yeah, I forgot.
X.
I forgot. What about now? I'll let people write minus 1s for once. There. What about now? There's a way to write x.
Is there any way to write 1? You're going to need 3 vectors to form a basis.
Oh, I need 3 vectors.
Okay, wait.
Wait. Let me try again.
What's the easy basis? What's the easiest basis?
X plus 1 and x minus 1.
You're way overthinking it. 1x squared x to the n. If I set this equal to 0, what is the only solution to this equation?
To do nothing.
Yep, that implies that a0 equals a1 equals
These coefficients. There, that's 0.
So what that tells us is that this is a basis. Okay, so when we think of...
I have a question.
Yes.
Is x plus 1 and x minus 1 a basis for 1?
They are.
How is that a basis? Is there a way to,
Yeah, give me any number, any polynomial that is linear. I can write it. I can write it in this basis.
You can write it in x plus 1 and x minus 1?
Yep. Like, let's say you wanted to write the number
ax plus b.
You want to write ax plus b? Okay.
Yeah, just to be general.
So let's say alpha x plus 1 plus beta x minus 1 is equal to ax plus b. So you get alpha plus beta x plus alpha minus beta equals ax plus b.
That means alpha plus beta is A and alpha minus beta is B.
So basically what it comes down to is solving a system of linear equations, right?
Yeah.
So once you have a basis for your vector space, then you can solve a lot of equations very easily. I went over a bunch of this with Matt, but it's not that important because the trick that I went over with you lets us skip a lot of linear algebra. So we're going to see a really amazing fact here. So let me give you another basis. This is the Taylor basis.
What's a Taylor basis? Oh, it's R. Is it just
1 x minus r squared all the way up to x minus r to the n.
I was thinking of x plus 1, x plus 1 squared, x plus 3, 1 cubed.
That's going to be an important example.
No plus, no minus.
We want it to be a minus because we want it to have a 0 at r, or not. We want all the terms that are not the first term to be 0 at r.
Oh.
So that's why we have a minus there. So someone proved that this is a basis for me.
Minus 1.
It could be minus 1.
And then that'll force the minus to become a plus. It will, right?
That will, yeah, it will. We'll do an easy example and we'll see our Pascal upper triangular matrix coming in. Okay, but someone proved for me that this is a basis. The proof is actually the exact same as the first one. So this is the fundamental problem that Taylor series answer. If I have a series I equals 0 to n of ai xi, how do I change the basis to rewrite it this way? So this is literally just a change of basis. So let's look at a special example that I think Ian will really enjoy. So example, r is equal to 1.
I was thinking r equal to minus 1.
Wait, r is equal to 1, n is equal to 3.
Wait, we can do r equals minus 1 next.
Yeah, buddy.
I want to see how it works from
I'll leave that up to you because I want to show you there's a pattern I want you to see with this particular example. So what we see is that if we have r equal to 1, n equal to 3, then we have a0 plus a1x plus a2x squared plus a3x cubed equaling b0 plus b1x minus 1 plus b2x minus 2, or sorry, b2x minus 1 squared, my apologies, plus b3 x minus 1 cubed. So if we expand this, that's going to be b0 minus b1 plus b2 minus b3 plus in parentheses b1 minus 2b2 plus 3b3x plus that's going to be a b2 minus 3b3x squared plus b3x cubed. So I'm going to write this as a matrix equation. So this thing right here, since this is in the basis 1x x squared x cubed, we can understand this is just the column vector A0, A1, A2, A3. This one is going to be a little bit more tricky. So let me rewrite this down here. We're going to have a change of basis matrix here.
What's a change of basis matrix?
This is what we multiply B0, B1, B2, B3 by in order to get back into the A0, A1, A2, A3.
Oh, so that's a special matrix you found?
So we need to factor this as a matrix. So if we just look at the first row here, that's going to tell us the first row right here. That's going to tell us the coefficients of our first first row of our matrix. So since matrix multiplication is row by column, we're going to have a 1 at the B0, a -1 at the B1, a 1 at the B2, and a -1 at the B3. All right. So if we move this down here, and then we look at this row right here, we're going to see that the coefficient of B0 is actually 0. The coefficient of B1 is 1. The coefficient of B2 is -2, then 3. All right.
This is starting to look like the upper triangular.
It is starting to look like the upper triangular one, except there's going to be a 1 here and a -3 here. And
then, there's a bunch of minuses, but if you remove the minuses,
okay,
you get the upper triangular.
This thing right here is almost U, right?
That's U.
U was our upper triangular 1 1 1 1 0 1 2 3 0 0 1 3 0 0 0 1, right? Almost. It almost is. Almost is, but it's got minus signs.
So how do we get away with the leap?
All right, so I'm going to show you a very amazing fact, and then we're going to prove it using the thing that I showed you already, Ian. But we're going to do this incredible linear algebra thing by not doing any linear algebra at all. This is one of the most beautiful.
Linear algebra. How do you do it without doing linear
algebra? You'll see. So let's actually do this matrix multiplication right here. So I'm going to take the matrix that we just found, our almost U.
Let's call it AU.
Or U primed?
No, AU. Stands for almost U.
Mathematicians like to use as few letters as possible. It is a little bit lazy, but this thing won't really need a special name because we're going to see something here that's going to give it a name already.
Okay, it's the inverse of U.
How did you get that so quickly, buddy?
I just guessed.
All right. So if we multiply this row by this column, we're just going to get a single 1. All right. So then let's move this column over. Oh, let me.
Yes, I got it correct.
Do this. So that's going to be 1 minus 1 is a 0. And then let's move this column over. So that's going to be 1 minus 2 plus 1 is 0 again. And let's move this over. I'm going to do the whole computation because it's worth seeing here, the magical thing that's happening.
The magical thing that's happening is that they're inverse.
Yes. That's kind of amazing though, right?
I didn't know that. I just guessed.
It's pretty amazing to me that this happens. The first time I actually saw this was a couple years ago. And the person who showed it to me did not have a proof that's as nice as the one I'm about to show you guys. And so to avoid doing this linear algebra, we're going to use the fact that polynomials form a vector space to do polynomial things on stuff that we'd otherwise consider to be matrix stuff. So this one is going to be 0 times 1 plus 1 times 1 is 1. And then the next one is going to be, let's see, 0 times 1 plus 1 times 2 times minus 2 times 1 is 0 again. 0 times 1 plus 1 times 3 plus minus 2 times 3 plus 3 times 1 is 0 again. And then moving down to the next row in the u primed, we can call this u inverse now, actually. So this is u inverse. This we're going to get 0 here, and then 0 here, and a 1 here. What's up, Ian?
What? Wait, that looks like u to the negative 1.
Yep, that means u inverse.
What's u to the negative 2 then?
It's equal to u inverse squared, or u inverse as matrices. Being able to compute powers of matrices is one of the most important problems in linear algebra, and I'm going to let your college class tell you how to do that, because you're going to do it so many times in your life, and you're going to get a computer to do it so many times in your life. I don't even do it by hand anymore. I use Sage Math to do it.
What's Sage Math?
It's like a coding language, but you can access it in your web browser.
Oh.
All right. So a related fact, which we're not really going to prove, but you could prove in a very similar way, is that if you did the lower triangular matrix,
yeah,
so zeros here, minus 1.
And the lower triangular matrix times its inverse is the identity. Nothing special.
Well, but this one, they actually are inverses, is the special part, because they have such a pleasing structure.
L and U?
Yeah, so this is L inverse and L is equal to
what is that big 0 and why did it replace most of the elements?
I didn't feel like writing 6 zeros, so I just put a 0 there to show. That's how a lot of people typically denote upper triangular matrices. Really, if someone just puts nothing at all.
A lot of people they'll know upper. No, those were lower.
Lower, my apologies. So like I could just do this and it would mean the same thing. We don't need to write zeros so much. But okay, so how do we prove this? How do we prove this? What that also means is
just like a triangle with nothing in it.
That also means that we could multiply. This is also a true matrix equation. If the first one is true, then the second one that I'm writing down is also true.
Wait, is that a triangular matrix?
Yep, so I'm just multiplying by this inverse on both sides, right? A2, A3, that's going to be equal to B0, B1, B2, B3. And this is the real money right here. We're going to be able to pull out a bunch of stuff right here. For instance, the derivative operator can be recovered just from this off diagonal. We can turn derivatives into a matrix multiplication using that thing right there.
Derivatives into matrix multiplication?
Yep, we can turn calculus into matrix multiplication. It is very useful.
But why?
Why? Well, it all comes down to being able to say that these two matrices are inverses, right? If we can do that, then we got a golden ticket. It opens the door for so much mathematics. So Ian, you've already seen this before, but let's do it again. Let's do
Let's do what again?
So we have the sum from I equals 0 to 3 of AI x to the I. And we want to write it this way. I equals 0 to 3 BI x minus r to the I, but without using matrices, right? Because that can be a little tedious for human beings.
I forgot how to multiply matrices. That's why.
It's all right. I will always do the matrix multiplication so that we can see examples of it. We want to do without changing matrices. We want, oh, it's starting to lag, to
It's starting to lag.
use Lagrange's trick.
You mean L'Hospital?
No, not L'Hopital, not that guy. That guy sucks. Let me just take a minute to hate on L'Hopital. Did you know L'Hopital did not invent L'Hopital's rule? You know who invented it?
Who did?
Bernoulli. Bernoulli was L'Hopital's tutor, and L'Hopital paid Bernoulli to write a book for him, and L'Hopital got to take the credit for it because he paid for the book. But L'Hopital was just some dude. Bernoulli was the one who came up with that rule. L'Hopital sucks.
Bernoulli.
Well, a lot of things are already named after Bernoulli. Do you remember Lagrange's trick? So let's.
No, I don't.
So we have a0 plus a1x plus a2x squared plus.
I don't remember Lagrange's trick.
You'll probably remember it when I do this first step. So step one, we're gonna, instead of doing linear algebra to invert this matrix, we're gonna do polynomial algebra instead. So step one, set. Oh, it's really starting to lag. X equal.
I think it doesn't like that it lost the town.
Yeah.
So it decided to lag.
Yep, that's exactly it, buddy. So step one, set x equal to x plus r. So we get a0 plus a1 x plus r plus.
You know what? I think you've been using active inspired too much. You need to move on to something new.
Honestly, here, let's see. Let's close Discord, close Spotify, turn off
Word.
Firefox, turn off Microsoft Word. All right. The only programs running on my computer are Zoom and OneNote. Let's see if this helps at all. All right, plus A3. Oh.
The only program running is OneNote. Well, if the only program running is
I said Zoom and OneNote, buddy. So what's step two? Do you remember step two?
Running is OneNote, then we'd not be in a meeting together.
Does anyone remember step two?
Step two. Expand.
Very good. I'm gonna collect terms at the same time.
Mathematical instincts. I really didn't.
Well, we have done it 2 days in a row now, buddy. So probably some buried unconscious memory was guiding you. So we have a0 plus a1r plus a2r squared plus a3r cubed plus in parentheses. Oh. Do you remember what goes in the parentheses, buddy?
I don't know. Wait, in the parentheses?
Yeah, so remember we said that this is a of x plus r. And we said that this first term was a of r.
And the second term was the derivative.
At r, right, times x. So if we collect terms, we actually do get a1 plus 2a2r plus 3a3r squared times x. And what was the next one? Do you remember?
The next one? Half the derivative, half of the second derivative.
Evaluated r times x squared. So that was a2 plus 3a 3r. So I guess I'll move this closer. X squared, and then finally plus a 3x cubed. Okay. And so at this point, this is what we have right here. We can factor this as the matrix 1r, r squared, r cubed, and then 0, 1, 2r, 3r squared, and then 0, 0, 1, 3r, 0, 0, 0, 1, and then we have times a0, a1, a2, a3. But this is equal to a of x plus r, right?
Closing every program help?
Yeah, kinda.
Or is OneNote still not liking you?
It's still not liking you. It's like when I get to a certain length in the note, then it decides to lag a lot. It's fine before, but
it's because you said you hate lost.
I'm not apologizing for that. That guy sucks. I'm not apologizing for that. So
but this then OneNote will continue to lag, eventually leading in OneNote closing and uninstalling OneNote.
I guess I'm just gonna have to deal with that problem when it comes up. So this is equal to a of x plus r though, and we really want a of x, right? So what we do is we set x equal to x minus r.
Yes. Wait.
And then we've written it in this basis.
What if you set it x equal to x minus r first, and then set it to x plus r?
You would get a series in x plus r to the kth power instead of x minus r, which would be 0 for all higher terms.
And we'd get derivative evaluated at x minus r.
R squared times x minus r plus a2 plus 3a cubed r times x minus r squared plus a3 x minus r cubed. So we've succeeded in writing it in the new basis, right? Just by using Lagrange's trick. Did both of you follow along with that? All right, so now I want to find the inverse of this matrix. Inverse of this matrix. This is almost our Pascal matrix, but this one is it has a bunch of powers of r in it now, whereas the example that we looked at did not have powers of r in it, and that's because in the example that we looked at, we were expanding around r is equal to 1. That's why this new matrix is more complicated. So of this matrix, okay. Being able to find the inverse of this matrix, there is an algorithm to always find the inverse of a matrix if it exists, and that is called row reduction. And row reduction is actually really important in a proof of our P is equal to LU decomposition that we had before. But we don't have to do row reduction to prove this. We kind of found a sneaky backdoor into this problem. So we have, let's do this again for n not equal to 3. So let's just say that a of x is now equal to this polynomial, the sum from I equals 0 to n. Oh, come on. I equals 0 to n of ai x to the I. So then a of x plus r is going to be equal to sum from I equals 0 to n of ai, and then I'm just going to use the binomial theorem right away. J equals 0. Wow, please just write 0 to I of I choose J times x to the j r to the I minus j. Okay, so what I would really like to do is collect terms of x. All right, yeah, so let's do it that way. So we're gonna have to be a little bit, how do I say? We're gonna have to use some counting to collect terms. So I equals 0 to n. Now, we want to collect terms of xi. So we're going to need a sum here. It's not clear what kind of sum this is going to be just yet. All right, so we're looking for the ith term. So let's just examine this for a couple powers of, or a couple of values of I. So when I is equal to 0, then we're going to have a0, and that's it. And no, that's not just it. We're going to have that for all the values of j. So that's going to be plus a1 times 1 choose 0, which is just 1, times x to the 0, because we want to have the 0th power of x, times r. Now, when I is equal to 2 here, maybe I should use different indices here, but we're looking at powers of x in this one. Maybe I'll use k here. No, I don't want to use too many variables. So it's going to go on like this, though. A2r squared plus ... Now, what about when I is equal to 1? So the first instance of a first power of x is going to be when this I right here is 1. And then we're going to have an a1 just times an x, because we're going to be looking at the second term in this second sum right here. So we're just going to have an a1, and that's, we're also going to have 1 choose 1 here. Now, when this I is a 2, we're going to have a 2 choose 1 here. So there's going to be a 2 there. And so that's going to be an a2. And then there's going to be a r to the 2 minus 1, which is r. And then the next one is going to be when this I is a 3, we're going to have a 3 choose 1 here. So that's a 3, a3 r squared, and so on. And when I is equal to 2, we're going to have just an a2 because the first power of x squared is going to happen when this I is 0. So we're going to see this Pascal thing popping up, but we could also write it this way. So this time it's going to be j choose I times a j. So j starting at I, because this is the lowest one to guarantee that such a power of x actually exists in the original sum. So we're starting at j equals I, and j is increasing. So we're doing j choose I because that is always going to be the place in the diagonal of Pascal's triangle that this coefficient belongs to. And times r to the j minus I here as well. And this is going up to n. This is from I. Okay, so this is an extremely important decomposition. We can think of this as the ith change in R. That's a summation formula for increasing dimension of Pascal's triangles. Yeah, that's basically it. Is we're just adding up each of the rows of Pascal's triangle, and those numbers are associated to the volumes of simplices, where a simplex is like the family triangle, tetrahedron, a five-pointed shape in 4D space, and so on. So yeah, it's definitely related to this. It's amazing how much the calculus and the counting are being brought together with a ton of other things in the linear algebra. But the important thing is I want to call this the ith change of A at R. This is a pretty important decomposition. I've never ever seen this in a textbook before. I had to just like brute force it to do the things that I wanted when I was first learning this stuff. So, you should write this one down. This one's pretty good. Ian, are you still there?
Yeah.
How much time do you have left, buddy?
1 minute.
1 minute. I think this is a good place to stop.
It's 5:30 to 6:30.
Yeah. I think this is a good place to stop. This formula right here, well, I'll just say one thing is if we then go back and set x equal to x minus, we're not done with this formula, but x equal to x minus r, then we get a of x minus r plus r is equal to this thing, I equals 0 to n, sum from j equals I to n, j choose I, aj, r j minus I, x to the I, sorry, x minus r to the I. This is also equal to just a of x because the r's cancel out. This is the Taylor series of our polynomial. So if you actually did the calculus to write this as the sum from I equals 0 to infinity of the nth derivative of a divided by n factorial evaluated at r times x minus r to the ith power. Maybe I should change this to an n. Let's change. Oh no, let's not have n here. Let's change this to I. Then it'll be consistent. All right. the ith derivative of a divided by I factorial evaluated r times x minus r to the ith power. This is the Taylor series, but what we did is we first set it up as a linear algebra problem so that we recognize a lot of facts from linear algebra coming into play here. And then we said, actually, Lagrange came up with the easiest way of doing this 200 years ago, 230 years ago, give or take a few years. And we can skip even the linear algebra part of this. We can just do the easiest trick in the world. So now that we have these matrices, we can do a lot of amazing things with them. And I think I will save that for next time. This is a good place to stop. So I'll take any final questions or comments you have or let you go.
Bye.
Later, Ian. I would really write down this formula, though, and convince yourself that it's true. This is a really powerful decomposition. I guess it's literally just the Taylor series, but you know. Okay, great. Anything else for me, Matt? I actually Ian is 8 years old. Yeah, Ian is a little intimidating sometimes, but he's pretty fun to talk to because he just gets a lot of things. Don't worry. Don't worry. If this was a shonen anime, you'd still be fine. You'd still be a character that doesn't die in a big fight. Ian literally just has the fox demon inside of him. Okay, so the that one problem I with the parallelogram, I was able to use the similarity argument to skip computing the height and get the same answer as well. So you can just recognize that these two areas are the same, and that lets you also get the same answer of 1200 over 7. Yeah, so yeah, that's the correct answer. It's the correct answer. 1200 over 7 is correct. Awesome. Hey, you enjoy your weekend, okay, bro? Later.